Will GPT-4 artificial intelligence be smarter than a human genius? OpenAI's GPT-4 is a next-generation large language model after GPT-3 and ChatGPT, and it's expected to use 100 trillion parameters. This jaw-dropping parameter count is possible because of recent artificial intelligence supercomputing advances from the Cerebras brain-scale chip cluster hardware, which is able to run a neural network with 120 trillion connections. For reference, the human brain has an average of 86 billion neurons. However, what sets GPT-4 and OpenAI apart from previous large-scale models is its use of sparsity at the core of its design. This means that even though the model has a parameter space of 100 trillion, the compute cost is likely to be lower than one might expect. This is because many of the neurons in the model will be inactive, reducing the amount of computational power required to run the model. From a layman's perspective, this means that the model will be able to keep a larger number of possible next words, next sentences, or next emotions based on the context of the input. In other words, GPT-4 is likely to be more similar to human thinking than GPT-3, as it will be able to consider a wider range of options when generating outputs. GPT-4 is expected to be both a very large and a very sparse language model, which is surprising given the history of OpenAI and its tendency to build dense models like GPT-3. Sparsity causes many neurons in the model to be inactive at any given time, which makes it become meaningless to imply a direct size comparison with dense models like GPT-3 and Google's Lambda. The use of sparsity in GPT-4 could potentially improve its performance and make it more efficient, as it would require less computational power to run. Regardless of its sparse nature, 100 trillion parameters would make it an extremely large AI model. When comparing to other sparse models like the Switch Transformer and Wudao, which only have a few trillion parameters, GPT-4 is significantly larger. Another huge feature is that GPT-4 is expected to be a multimodal language model, capable of accepting a variety of inputs, including text, audio, image, and possibly even video. This is an exciting development, as it would allow GPT-4 to generate outputs in a variety of formats. Given the already impressive ability of language models to generate human-like text and the recent advancements in audiovisual generative artificial intelligence, it makes sense for OpenAI to continue exploring this venue with GPT-4. It is not yet known exactly how GPT-4 will be able to handle these different input modalities, but use of multimodal input and output is an important direction for the future of AI, not just because the human brain processes information from multiple senses, but because the world itself is multimodal. When artificial intelligence is able to process sight, sound, touch, smell, and even taste-related inputs, it will be able to effectively interact with the world and understand the complexity of human experience. This is why GPT-4's expected ability to accept and generate multimodal outputs is an exciting development. Another interesting aspect of GPT-4 is that its expected training cost is around $6 million, which is significantly lower than that of its predecessor at $12 million per training run. This suggests that OpenAI has found a way to reduce the cost of training large language models. There are a few possible ways that this could be achieved. One would be if OpenAI has improved its optimization at the software level, allowing it to train the model more efficiently. Another possibility is that GPT-4 is able to take advantage of faster chips or hardware, reducing the cost of the computing power required to train the model. Another potential explanation for the reduced training cost of GPT-4 would be if OpenAI partnered with Cerebras to train their model on their newest supercomputer. This would allow developers to avoid the use of optimization heuristics, which can hinder performance. The CS2 is so large that it would be able to train a colossal model like GPT-4 without the need for such tricks. GPT-4 from OpenAI is expected to be released sometime in January or February of 2023. With extremely large language models that have more connections than the human brain, artificial general intelligence could be closer than we currently expect. Breakthrough soft robotics device heals itself after being stabbed. Northwestern University researchers have created a quadruped robot that can stop moving when it is damaged and wait to be repaired before continuing. This is a significant development for soft robots, which can change their shape to imitate biological tissues like muscles for use in prosthetics, but are vulnerable to damage. The new robot is able to detect damage and repair itself. The X-shaped robot, which is just over 4 inches in length, moves using compressed air that is pushed through its body, which enables it to undulate and lift its 4 legs. The robot's top is coated with a self-healing layer of sensors made from a transparent, rubbery material that tracks its motion. When the sensor is cut, its exposed sides become chemically reactive, enabling it to repair itself and continue functioning. The researchers tested the robot's ability to detect and respond to damage by repeatedly poking a sensor on its leg. The soft robot stopped moving for about a minute after each poke to allow the sensor to heal and then resumed moving. In another experiment, the researchers poked the sensors on the robot's legs one at a time. After each injury, the robot stopped moving to allow the sensor to heal, and then changed its gait in response to the damage. In the future, soft robotics devices with self-healing parts could be used in hazardous environments, and the self-healing sensors themselves could be integrated into wearable devices like spacesuits to detect and respond to damage from space debris. New Memristor learning system reduces power for AI training by 100,000 times. Deep learning models have been shown to be very effective in making predictions and solving real-world tasks that involve analyzing data. However, before they can be used in real software and devices like cell phones, these models need to be trained extensively in physical data centers, which can be both time-consuming and energy-intensive. Researchers at Texas A&M University, Rain Neuromorphics, and Sandia National Laboratories have developed a new system for training deep learning models more efficiently and on a larger scale. This system, described in a paper published in Nature Electronics, uses new training algorithms and Memristor crossbar hardware, which allows for multiple operations to be performed simultaneously. Because traditional backpropagation algorithms were not well suited to the system the researchers were developing, they created a new co-optimized learning algorithm that takes advantage of the hardware parallelism of Memristor crossbars. This algorithm, which is based on the differences in neuronal activity observed in neuroscience studies, is tolerant to errors and is able to learn even from sparse, poorly defined, and noisy information, like the brain. This brain-inspired and analog hardware-compatible algorithm could make it possible to implement artificial intelligence on edge devices with small batteries, eliminating the need for large cloud servers that consume a lot of electrical power. This could make it more affordable and sustainable to train deep learning algorithms on a large scale. The researchers showed that their approach can reduce the power consumption associated with artificial intelligence training by up to 100,000 times compared to even the best current GPUs. The researchers plan to study how these systems scale to larger networks and more difficult tasks. They also plan to study various brain-inspired learning algorithms for training deep neural networks and determine which of these perform best in different networks with different hardware resource constraints. They believe this will not only help us understand how to learn efficiently in resource-constrained environments, but it may also provide insight into how biological brains are able to learn so efficiently.